Okay, hello. This is Tosin. My name is Tosin Alabi. I'm a student at the University of Bordeaux currently, and I'm from Ilorin, Nigeria. Um, I am currently trying to make a bunch of videos about things I'm learning, things I find a little bit interesting, because I realized that when I make videos about things and when I actually like make do a little project about things I have found interesting, I tend to remember them more easily. And I also have gained a lot from watching a lot of videos over the years of people just explaining things that they found interesting. And I should also, I think, make some and also help people or people that also want to maybe get into some of the things I find interesting, maybe make their journey a little bit easier as well. So that's the purpose of these videos. And this is one project out of, I don't know, a lot of projects I plan to do in the future about a lot of things that I find interesting and difficult, or interesting and easy, but and I'd like to like talk about them. So this is the first one. So it's on my foray into explainability. That's I always see this like this I don't know, beautiful feature visualizations of what convolutional neural networks learn, and what they're actually doing, and what is the reason why they are actually doing like various things. And I also wanted to like let me also try and like look into the topic and figure out how to perform these visualizations. And that's why I'm presenting what I did so far, and hopefully this helps you. Okay, so I think we should first talk about confidence. That's CNN's extremely popular in the deep learning field right now, extremely popular. They are everywhere. As long as there is a grid or a repetitive structure or things in structure, you can probably use convolutional neural nets, and they work very, very well. And but the problem is that they are seen as black boxes majorly. They are usually seen as black boxes. They are very complicated. They have a lot of parameters, and usually most people do not know why they make decisions. So they are seen as black boxes. Unlike other easier models like maybe the linear regression, they are seen as black boxes. So the field of explainability, they try to produce they produce they investigate methods that interpret these results and allow for you to trust in your models. They they allow you to they help build more trust in models. And they they let me give an example. An example which I heard about on a podcast was about police officers that are arresting people based on what a model tells them. And if they don't actually know the reason why the model tells you to arrest this person, then there's a big problem. Or if, for example, a class has sets a cap for 25 people in the class because the model tells them that you can only have 25 people for you to have maximum efficiency. Of course, the parents of the children that are in the class would actually complain, like, why must it be 25? Why not 26? And these are important questions that need to be answered for users to gain trust in what machine learning models do. And machine learning models have been deployed everywhere, from agriculture, medicine, production, product recommendation, everywhere. So explaining them, I think would go. What I am explaining them would ensure that users use them more, and also like there's more trust in your models. And it's a huge field, so big. People do PhDs, and there are so many like right now there are so many investigators, professors that are in the field. It is super big field. And I think it's a very interesting field, I think. So let's let's that I was interested in the feature visualizations, and some of there are two methods I was able to try my hands on, which was activation maximization. Sorry, that's an error. Activation maximization and the gradient-based class activation maps. So activation maximization is actually the one I saw. I always see in YouTube videos where they take random images and they use them to produce and they use those random images to show what a particular model is viewing at a particular time. And it's based off of the gradient ascent method. I first heard of gradient ascent when I was watching a YouTube video by Ian Goodfellow. He was giving a talk on gradient ascent, I think a long time ago, and he talked about it's a field that it's used in adversarial creating adversarial examples, and but he also finds good use when you are trying to figure out exactly what a filter is looking at. What does it respond to the most? What does the filter give its maximum activation for? And the way it works is instead of normally, like, neural networks are trained via gradient descent or other methods, using other methods, but generally via gradient descent. But instead of using gradient descent, you are trying to increase the activity. You're not trying to you're not trying to change your model. You're trying to change your image. So looking at the gradients for a particular filter, you try to move in the direction that you try to move your image in the direction that keeps increasing this gradient. And this is a quick formula for that. So if this is your image, then this is your image, this is your gradient for a particular filter at a particular layer. You this is a learning rate, which adjustable learning rate. You perform a bunch of iterations and you get a new image that has moved in a direction that increases the that would increase the gradient, and at the end of the day you'd get an image that gives like a very high gradient for that particular filter. And a image that gives a very high gradient means that that is exactly what the filter is looking for. The filter is looking for things that look exactly like that. And yeah, so this was an example from the lecture by Ian Goodfellow. And the the I there's some quick examples you can find in Keras, Keras examples by Francois Choulette. You just have to search Keras examples and you will find it. For this is for Grad-CAM. This is the activation maximization. Okay, so this is literally the one from Francois Choulette, the correct examples, and the main thing I wanted to show here was was the this what the example was showing was they took a pre-trained network from ImageNet. It was ImageNet. It was a ResNet 50. In case this is how a ResNet 50 looks. It's a bunch of comms with a bunch of skip connections, or like, no, residual connections, I think, with a bunch of residual connections. It's a method to ensure that weights pass from go along for very, very deep convolutional neural networks. It helps the transfer of gradients to be a lot better, and it works very, very well. It's like the de facto standard for transfer learning. And this is how it looks majorly. So he took a pre-trained network on ImageNet, and he performed gradient ascent on it. And the gradient ascent, he used it. He was checking like what each of the conv filters actually responds to, because there are a bunch of conv filters. This is 64, 64, 64. There are a bunch of them, and you have to each of them respond to different patterns generally, and you want to know which patterns they respond to the most. So um, what I actually want to show here has to do with the in has to do it over here. Yes. So you you compute your loss and compute your gradients according to the image in which you have currently, and then your new image was based off learning rates, adding the previous image with the learning rates plus the gradients. But then you are not performing any training of the model. It's just gradient ascent step. It's just, and which is just the image, an image plus the image plus learning rate times the gradients which you got using you got the gradients using get using the gradients of the loss to the image. So I don't think that's like yeah yeah. Um, um the that it's not um the the images they look really freaky a little bit. I will show some of them. So I did the experiment for an earlier layer, and I got majorly a bunch of color filters. Then in the middle layer, I got some more complex like patterns, and towards the end became even more complex. I couldn't read them like exactly, but I can see this like I could see semblances of like I don't know animal like stuff, but I'm not exactly each of them look very I don't know quite complex. So but you could see the beginning of a bunch of patterns, but not exactly clearly. But it was at least good to realize that the gradient ascent step helps to actually visualize like the things that are inside the network. I took that exact example from that from the Keras examples, and I just tried it on MNIST. There's I built a small layer with two convs and two dense layers, and I tried it on MNIST directly. I do know that that example is not I don't know perfectly exact because there were some shortcuts I think that was done in the example. Um, the especially how the way they got the way you get the way you process the images. Generally, there's supposed to be like some constraints on your gradient ascent step, but instead of adding constraints, the examples perform the way of the processing the image. I'm not exactly sure if this would affect the results. For the resonance, it doesn't affect the results so much. But for MNIST, I think it might have affected the results a little bit. So this for the very first conv layer, this was what I got. I noticed there was some noise, like some of the filters were just responding to plain noise, which was like weird for me. But I could see some horizontal lines, some vertical lines, and I only graphed about 16 filters. There are a lot more. There were like I think there were about 64 32 filters for each of the convs, but a lot of them seem to just be responding to noise. Some of them it looks like I don't know the beginning of a number. I think this looks like seven a little bit. This looks like a little bit like four. It looks a little bit like I don't know maybe I don't know three or a two. But something that was revolutionary, something that was new to me was some of them just seemed to respond to like noise, and it was well at least it was a good way of seeing like just was just for me trying to see how it would work on MNIST. And then I went to class activation maps, which yeah, I think this the one of the popular feature visualization methods as well. That's you you visualize for a particular example for a particular example, what does the model use to actually what does the model use to actually make decisions. For this was from the original paper by by Zhou et al. I hope I didn't butcher the name. I'm very sorry, Mr. Zhou, Mr. Zhou, Mr. Zhao. I'm very sorry. So this was from the original paper, and they were looking for the Australian terriers, and the main idea for that was they did a global for the very last conv, because the convs are what gets your convs convs they understand space, they understand spatial features, they understand images in terms of how they are in space. Usually the dense layers are for classifiers generally. So for the very last conv, each of the very last conv, this is what helps. They are the ones that extract the features, and you want to know what features were used for a particular image. So they perform global average pooling. They get a bunch of weights, weight one, weight two, all the way to weight n. Then those weights, there was a weighted average that was done for each of the weights multiplied by the by it by the feature map that actually got that particular weight, and they perform the weighted average of that, and with that you can see exactly where the image is looking for a particular class. But there were some drawbacks, because you needed to get what these weights were, the what that's W1, W2 all the way to WN, and you had to actually train your network to get exactly what these weights were. Not only that, there were other drawbacks as well, and one of the I think the popular solutions to those drawbacks was the gradient-based class activation maps, which is the other test that we worked on. Wow, this video has gotten long, 16 minutes, and it was designed to solve the problems that I told you about, and all the main idea about it all was that instead of using weights, you could use the gradients, and you could instead of using the weights of the instead of using the weights that you saw over here, a generalization on those weights was actually each of the gradients, and what the gradients for a particular class with respect to the particular feature map actually also can be taken as the weight. And what that helps with is that it ensures that you don't need to retrain. It ensures that the idea can be applied to more than just um, more than you don't have to perform. You don't put constraints on your network, such as the having to perform global average pooling. And I, I I don't think I should talk about maths unless maybe I'm wasting time. Okay. And these were some of the examples straight from the Keras examples as well. With I think this time was exception, and they wanted to check on African elephants and which part of the image. So they passed this particular image, and they perform Grad-CAM, and it gives you that this particular part of the image is what the network looks for to say that this is an African elephant. They also passed an image with a dog and a cat, and this was the class activation map for the dog and the class activation map for the cat over here. So I took that example and did the same thing with MNIST, and it worked just as expected. MNIST is not a very difficult data set, because there's not so much things that that can distract the network, but it works just as expected. Nothing like mind breaking there. But I also wanted to perform like both activation maximization, as well as gradient based class activation maps on a custom data set with a custom problem. So I there's this there was this data set I saw online here on Cargo. Yeah, so it was just something with potholes and it was a good road versus bad road classification. And if you live in Nigeria, you know there are a lot of bad roads and good roads. So it was a good road versus bad road classification. These are some good roads. These were examples of good roads. It wasn't like focused a focused example, such that there was a lot of distractions. You can see, for example, this place has a bunch of signboards, a bunch of traffic lights, the river. It wasn't a focused example, but it was enough. It was me trying to perform this or use this for. It was more than enough. This was just examples of potholes in the road. It's a pothole, very focused. Other potholes over here, and yeah. So the idea was I was going to try both class activation maps and gradient based both gradient based class activation maps and activation maximization. I trained a small network that was just three convs, flatten, dense, nothing special, I think. Then upon the the test accuracy was around 88, 89%, but it was not the best. I probably can get better, but it was enough. And I performed the gradient ascent on the gradient ascent was first done, and then after gradient ascent was done, then I performed the grad cam on the particular network as well, feeding in images and examples and getting solutions. So just the process was not difficult. That's build a small network to classify between good roads and bad roads, um, perform activation maximization, perform GradCam and see how the results work. So this was the activation maximization, and this was the very first layer, color filters, some patterns as expected. But something I noticed was I expect there to be a lot of blue and maybe, I don't know, the road kind of blue, but then there was like a lot of green. I did that for the second and third layer as well. Second layer, you can start seeing patterns that look like the roads or cracked roads, spots, but then they kept being this green. This is noise. This is just noise, which still shows that maybe I don't know, maybe I didn't train it perfectly. Maybe I used too many filters or something like that. And it was I always just use like a lot of filters whenever I train. This was good for me because it made me realize that I'm using too many filters whenever I train. I should probably don't always just go for broke because it's not necessary, it may not be totally necessary. So the main thing was like there was this abundance of greens and I was worried about them. The last layer even had more complex patterns. You can see some really road-like patterns over here and this green again. So I went forward and did a lot of GradCam as well. So it worked like as expected, I think. For this particular image, you could see it was looking at the roads. It was looking at markings as well on the roads. And for the crack potholes, it was looking at things that look like cracks, lots of like hole kind of things, as well as the cracks around it, cracks, markings, the road. But then I also noticed that the network was cheating. The network was cheating. It wasn't like a lot of data set. The data wasn't focused. It wasn't like to the road directly. So my network was associating the vegetation around it, green vegetation around the two good roads, which makes sense. A lot of the green vegetation you see are on maybe highways. Usually highways are usually good ways. It was not just that, it was associating signboards as well to good roads. Small data set, whenever it saw signboard, good road, it wasn't really looking at the vegetation and signboards were good roads as well. So that which makes sense in the sense of it. You would have a traffic light, or usually you'd have like a traffic light at points in which there is a good road or something like that. And the data set, this was like a bias in the data set as well as the data set not being enough or on the data not being focused on the road. So it was something that I don't know was eye-opening and I thought it was very interesting. So I just wanted to share it. There were some conclusions. Another thing I thought was important was the fact that I think it's probably nice to use multiple explainability methods for a particular problem. That maybe if you use like maybe multiple of them, you get even more like good explanations. and there's something, maybe some questions which people might have. I don't know, maybe some kind of frequently asked questions. One of them was, are there other explainability methods? Yes, there are a bunch of them I saw. There was line, there was partial dependence plots, there were concept activation vectors, there were things that had to do with data, there was shapely values. There were a lot of them, and there are a lot of examples of them online as well. So yeah, I think getting into the field is not it's not very difficult. I saw the Lucid Chat. TensorFlow has a visualization toolbox called Lucid Chat, but it's only for TensorFlow 1. You can on Colab, there's a way to use a magic value change to TensorFlow 1, but it was also very good. And it's something that I think anybody can get into. And if you build a network, I think it's maybe, if you have some extra time, it would be really cool to just quickly figure out what is doing. The how do you group explainability methods was another question. And there were groups such as local versus global. That's local only explaining maybe a particular image or a part of the image, while global explaining like the full class. There was model postdoc versus inbuilt. So there are some models that have like inbuilt explainability, such as like it's debated, but things like decision trees, linear regression, and other ones such as like CNNs. You have to perform this is like a post post hoc explainability methods. There was also like the differentiations based on whether you're explaining the data, whether you're explaining the results. For example, Grad-CAM explains the results, why a particular image why a particular image, why do we get this particular prediction for a particular image. That's explaining the results. GradCam, I think, falls under that. Then there is also explaining the model. I think activation maximization falls under that. What does a particular filter looks like? Those were other questions. Then maybe a question someone that is also beginning might have is it only for computer vision tasks? No, not at all. For NLP, for recommendation, for anything you can think of, there are methods that perform explainability. And the textbook I was recommended to by a friend was Samek Veodadi, Hansen, and Muller, the explainable AI interpreting, explaining, and visualizing deep learning methods. It doesn't have a lot of pictures, and I generally like a lot of pictures, but the explanations, I think they were I use it as a reference. They have been very good so far. So yeah,